So this is a second video then on kinetic energy and work and energy, and we want to find and calculate the kinetic energy of a car. A typical car, 2100 kilograms, that's moving at a velocity of 55 miles per hour. So one of the first things I wanted to do was convert miles per hour to meters per second. So I thought it would be useful to get a little memory recollection here of how we do that. We want to convert 55 miles per hour to meters per second. So we got miles per hour. We know that 1 mile is 5,280 feet, I believe. 5,280 feet per mile. And then we have to get rid of feet, so we have 12 inches per foot. And then we have to get rid of that, so we're going to have 2.54 is the, I always remember 2.54 centimeters are in 1 inch. And then of course there's 100 centimeters in 1 meter. And then of course there's, we want to get rid of hours. 1 hour is 3600, I believe, seconds. So when you do this, you see you have all these units canceling out along the way here. Hours are going to cancel with hours here. And when you do that, you're going to find for 55, I got 24.6 meters per second. Now we can find the kinetic energy. So the kinetic energy, we've already said, was 1/2 mass velocity squared. That's our kinetic energy formula. So we're going to have 1/2 of the 2100 kilogram object, and that velocity is 24.6 meters per second. We're going to square that. And if we do that, we find out that our kinetic energy comes out to be 634.8 kilojoules. Now I thought it was interesting to observe what would happen if we increase the speed from 55 miles per hour to, say, 75 miles per hour. So 55 is the speed limit. Someone wants to go a little bit faster. They're going to do 75 now on the Garden State Parkway. And in that case, we want to find out what is the new kinetic energy. Well, what I did was I took this 75 miles per hour and I converted that to meters per second. And when you try and convert that to meters per second, 75 miles per hour, did I write it down here? I don't know whether I did. This may or may not be correct. I apologize. I think it's 34 something. I think it's 34 point something. I can't remember. I didn't jot it down, unfortunately, but it's I think it's that's like 34 meters per second. You can do the math. It's the same math. You're just going to plug in the 75 up here, go through the same routine. You're going to find out what it is in meters per second. I believe it was 34. But anyway, I do have this number right. So when we have the new kinetic energy, is going to be 1/2 of this 2100 times this new kinetic energy here is going to be 34 point whatever it is, but that's going to be squared, and we find that that actually goes up to 11. Well, you know what, let me just do it and I'll be right back with you. Okay, so it was 34 when it come out to, and because I just looked that up. This then comes out to, what is this new kinetic energy comes out to? 1180.3 kilojoules. Now look at the difference between this number and this number. I figured that percent increase, it's about a 46% increase in kinetic energy. So just going 20 miles per hour more resulted in almost twice the kinetic energy. And if you remember kinetic energy as the ability to do work, how it's related to work, you just increased your chances that if you got into an accident, the amount of force applied to a distance that would be acted upon that car would be almost twice the amount going at 55 miles per hour. And that is because the speed is squared. So it's going to go up at a squared rate. It's not linear. So as you increase speed, there's a nonlinear correspondence, and the kinetic energy then is going to go up as the square. Okay, so next time what we're going to do is work another problem. It's going to be a problem from the book, and we'll do it next video.